All right, so last week we went over all kinds of situations where Newton's second law applies. We talked about system questions, okay, which could be anything involving more than one mass. So we talked about masses hung over a vertical pulley. Okay, we talked about masses connected, okay, by a pulley where one was horizontal and the other was hanging over the edge, okay, which is going to be like the lab we're going to do tomorrow. We talked about inclined planes, okay, and the different forces that are always present inside, gravity always being directly downward, okay, normal force, which we haven't used yet but might get to this week, okay, being the adjacent side, okay, these two angles being identical, okay, this side being F parallel, which is the vector sum of the two forces involved in the plane, okay, and then any other forces like an applied force pulling up or friction, okay, resisting in whichever direction, the opposite direction of the box's movement. Okay, we talked about those last week. We talked about having to draw tail to head vector diagrams for forces. We've basically gone over pretty much all the situations in which Newton's second law could possibly apply, including static condition examples where, you know, we had a sign that was suspended by two cables and it wasn't moving and we had to find the tension in the cables. All right, there's variations on all of those things, but we've kind of seen at least how they all work. All right, so the plan for this week, today specifically, is to work on a few examples of those. Okay, tomorrow do our lab, and then Thursday kind of see where we're at, possibly introduce friction, okay, talk about how it works, okay, and then Friday possibly looking at Newton's third law, and then an assignment next week. Okay, is probably where we're going to head to, because I would really like to be done everything to do with Newton, even including the third law, before Easter break. Okay, then we come back after Easter break and we start on to work energy theorem and conservation of energy. We will probably after Easter break have 2 weeks left in this unit. Okay, so probably shortly after Easter, expect that we'll be looking at the Unit 2 exam, okay, because that'll be closer to the end of April. Okay, which is about where we said it would be. So we're right on track, which is good. All right. Okay, so what I would like you guys to start off with, since we're not having a quiz, even though it's Tuesday, is I would like you to look at questions 20 through 25 on the first Newton worksheet. Okay, so this is at the top of page 3 in the digital workbook. I'll leave the questions up here on the board, but if you'd rather have them on your phone, okay, that's where they are. Answers are in bold. I'll give you some time to get ahead of me, and then we'll look at a few of those, okay? They start off with a vertical frictionless pulley, okay, so we've done something like that. We got an elevator question, another elevator question. We got some inclined plane stuff, and then we'll move on to some vector questions after that, okay, just to kind of refresh after a 4-day break. If you got questions, just let me know. Okay, so on our first one, we have a vertical pulley. So we have the pulley here, and we have the two masses hanging over it. Okay, one below, slightly below the other, or even if they're at the same level. Okay, so we have a 1.5 and a 2 kilogram mass. So if this is going to work, this is probably the 1.5 kilogram mass, and this is probably the 2 kilogram mass, although it doesn't really matter. Okay, the 2 kilogram mass is just going to be the one that goes down, and the 1.5 obviously the one that goes up. All right. So what we have to do is calculate what forces, or identify and then calculate what forces are going to be present in this system. Okay, and the force is gravity. It's just acting in two places. It's acting on both masses. It should be a lot longer. All right, so we're going to have a force of gravity here, and we're just going to go m times g, so 2 times 9.81 is going to be 19.62 newtons, and 1.5 is going to be 14.71. Is that right? 715. Okay, newtons. All right. Those are the only forces. It says it's a vertical frictionless pulley, okay? And we have to assume that the rope connecting the two is massless, otherwise we would have to factor its mass in, okay? So we're just going to simplify this. In the end, this system has a mass of 3.5 kilograms, and it is being pulled in opposite directions by opposing forces. 14.715 newtons and 19.62 newtons. Everybody all right with that? Okay, so what do I do next? Right, find the vector sum of the two forces. They're in direct opposition, so all I have to do is subtract, and that should be 4.905, right? So F net, okay, will be 19.62 minus 14.715, which should give me 4.905 newtons. Okay, now that I know my net force, can I calculate the acceleration of the two masses? Yeah. Do I actually calculate the acceleration of the two masses, or do I the acceleration of the system? The system, right. Okay, so I'm going to calculate the acceleration of the system by taking that F net and dividing by the mass of the system. Okay, so that'll be 4.905 divided by 3.5 kilograms, which is going to give me 1.4 meters per second squared, and then I can look at the situation and apply vectors to do A and B. The 1.5 kilogram mass will go up at 1.4 meters per second squared, and the 2 kilogram mass will go down at 1.4 meters per second squared. Questions?
So you'd still be right if you said the 1.5 kg was negative and the 2 was positive, right? Because as long as one's positive and one's negative, it'd still be right.
You would have to define those directions.
Oh, okay.
Like, because down isn't usually positive, so if you did that, you'd have to say down equals positive, just so that I knew. You're better off to say down and up.
Yeah.
Rather, I mean, I probably shouldn't have done this. I should have said up and down if I was doing a better job. But this Tuesday feels like a Monday, and that's my story, and I'm sticking to it. Hey, how are we doing on the second one? We need a little bit more time on that one? Okay, so last week I told you that this is a trick that often gets played with elevator questions. They tell you about this ridiculous situation where someone's standing on a bathroom scale in an elevator because, well, people do that, I guess. Okay, now what the scale always reads, whether the elevator is moving or not, is how hard the floor is pushing back on your feet. So if the elevator isn't moving, it's telling you your weight because you push down on the floor and the floor pushes back up with a force equal to the force of gravity. As soon as the elevator starts to move, the floor is either going to have to push harder or less than the force of gravity, depending on which way the elevator is moving. So what the scale always reads is how hard the floor pushes. So in this situation then, we have an elevator that has it's just the person in the elevator, okay, that has a force of gravity of 725 newtons. Okay, and that's the trick. They don't tell you the mass of the person, they tell you the weight of the person. When I said this is a trick I can also play on you with an inclined plane question. Right? I can tell you the box is this many newtons, and I'm giving you its weight, the force of gravity, not its mass. Can I find the mass of this person?
Yes.
Yeah, I just have to divide that by what?
9.81.
Okay, am I going to need that?
Yeah.
Yes, I am. I'm going to have to calculate the acceleration later, so I might as well calculate the mass right now. Mass is going to be Fg over g, so 725 divided by 9.81 will tell me the mass of the student, okay, anywhere. Okay, so the person's mass is 73.9 kilograms. Alright, I'll need that for later. Alright, the other stuff I know is that when the elevator starts to move, okay, upwards, the scale reads 775 newtons. Okay, so I can also put in here that this is 73.9 kilograms. Alright, can I calculate the net force? What's the net force? 50 newtons. Okay, I got 775 up, 725 down. All right, so F net then is 50 newtons up. All right, well, acceleration equals F net divided by m, which I calculated conveniently earlier. Okay, 50 divided by 73.9 with all the decimals. Right, and I should get, yeah, 0.677, because I do have 3 significant digits there, meters per second squared up. That should have a vector on it. Okay. Okay, so in the end, there wasn't a lot of really tricky math, but there were a few tricks in that question for sure. Right? And those are always things we have to watch out for. If they tell you something in newtons, it's a force. Okay? And if they're referring to a person or an object, it means that's their weight. Okay? If they're referring to a force, like an obvious pull or a push from something, okay, then you can put it on your free body diagram as well. Okay? Anytime you get something in newtons, it's a force. Okay? We don't want to get it confused with mass when they're telling us, okay, about a person or an object. Okay, give you a few more minutes to get ahead of me again here. Okay, so you got another one that's kind of an elevator question, okay, but is going to also involve a little bit of acceleration stuff, okay, as well. Okay, so on 22, we have an elevator again, okay, but as soon as I change the wording to not include elevator, sometimes it gets a little bit confusing. It's not as obvious that it's now an elevator. Okay, so an 8-kilogram object is pulled upward by a rope. Okay, the tension in the rope is constant at 95 newtons. What other force is present?
Force of gravity.
Force of gravity. Okay, force of gravity is the reason I have to pull with a rope, otherwise I wouldn't have to do anything. Okay, so 8 times 9.81, 78.48. Okay. All right, so I've got my force of gravity and I have my tension that's pulling up. All right, they want to know what the velocity of the object is. So I'm looking for VF. I know VI is 0 meters per second. Okay, after 1.1 seconds, what do I need? If I want to calculate final velocity with those 3 things,
Acceleration.
I need acceleration, yeah. Can I find the acceleration?
Yeah.
All right, first thing I got to do is find F net. That'll be 95 minus 78.48. Okay, so we got 16.52 newtons up as our net force. Then we can calculate acceleration, 16.52 newtons. Okay, divided by the mass of the box, 8. All right, so we got 2.065 meters per second squared up. Okay, now we can calculate VF, and we would just use this, A equals VF minus VI over T. Okay, and we would manipulate for VF, so that'll be A times T plus VI, which is 0 anyway, okay, equals VF, so we just have to go A times T, right, which is going to be 2.3 meters per second, because it's 2.065 times 1.1. All right, that's a pretty typical type of question that I could give that would have a part A and a part B. Okay, if I give one that's got a part B that's an acceleration problem, okay, generally the first part is fairly straightforward. Okay, as that one was, it was 2 forces directly in opposition to each other. All right, questions on that one? Okay. All right, so now you're on to the inclined plane questions, and in each one of those inclined plane questions, what do I tell you about the box?
The force of gravity.
Right, I tell you the weight of the box, not the mass of the box. But of course, if you have the weight, you can find the mass. Okay, question in the water. Yep. All right. Okay, give me a few minutes to get ahead of me again. All right, so on 23, all we have to do is find F parallel. Okay, so it's pretty simplistic. We don't actually have to do very much else with it. Okay, so we got a 25-degree angle. Okay, we have our 445 Newton box. We don't even have to calculate the mass for this one because we don't need it. Okay, we're just dealing with that internal triangle. So we know that this side's 445 newtons because it's the force of gravity. Okay, we've got this side here, which is F normal, and we got this side here, which is always going to be F parallel, which is the vector sum of the force of the plane pushing perpendicular and the force of gravity pulling the box down into the plane. Okay, so to find F parallel, it's the opposite side. I have the hypotenuse, so F parallel is always calculated by taking the sine of the angle, in this case 25, and multiplying it by the force of gravity, in this case 445 newtons. And when we do that, we should get 188 newtons down the ramp. Okay? Now, most inclined plane questions do not end there. And by most, I mean that's about the only one I've ever seen that ends there. Okay? Most of the time you have to go somewhere else from there, like calculate the acceleration, or the box is being pulled up the ramp, or something along those lines. Kind of like the other ones that are on this sheet. Okay, questions on calculating F parallel, which you have to do for basically every single inclined plane. All right, give you a few minutes on 24 and 25 here. We'll go over those, and then we're going to look, we'll take a little break, and then we'll look at some vector ones, okay, that'll require us to do some vector diagrams. Okay, so the thing with 24 is we're still dealing with a frictionless incline, which is actually kind of simpler than some of the ones we've done. Okay, it's a 30-degree angle. All right, we know the mass, or the weight of the box is 325 newtons. Now, because we're calculating acceleration in this one, that's what they want the final answer to be, we do need to calculate the mass. Okay, so we're going to have to go Fg over g, okay, 325 divided by 9.81. Okay, so we got 33.13 kilograms, okay, which I could write there. Okay, 33.13 kilograms. I'm not going to need normal force, but I am going to need F parallel because it's also going to be the what force? It's also going to be the net force. There are no other forces. There's no friction. There's no one pulling it up the ramp or anything like that. Okay, so F parallel becomes the vector sum of F normal and Fg, which is the only thing happening in this question. So all I have to do is divide 325 by 2, so I'm looking at 162 and a half. Is that right? I think that's right. Yeah?
Wait, so you didn't have to use sine?
I did. Sine of 30 is 0.5. Sorry, shortcut. That's why I pick 30 degrees so often. You ever notice that? I pick 30 degrees all the time so I can show off and make it look like I can do trig in my head, but I can't. Okay? So yeah, if I go I shouldn't skip steps. F parallels the sine of 30 times 325, which is going to be 162.5 newtons down the ramp. Okay? So that's also going to be my net force because it's the only force acting. Okay? So now I can go acceleration equals 162.5 divided by 33.13 kilograms, okay? And that will give me the 4.91 meters per second squared. That would be the case for any 30-degree frictionless incline. 1/2 of the acceleration due to gravity is present at 30 degrees. Okay. All right, questions on that one? Okay. And for 25, okay, this one has friction. So this one we have to do a little bit of that sum of all forces at the end in order to get the force of friction. How many people have done this one? All right, so we got okay, our 40-degree incline. All right, we got our box here, 435 newtons. Okay, is our force of gravity. Okay, we're going to need F parallel. 40-degree angle. We're also going to need the mass. That's going to be important. So 435 divided by 9.81, okay, 44.34 kilograms. Okay, we are looking for the force of friction acting on the box, which is that way. Because naturally, the box would want to go this way because of F parallel. There are no other forces mentioned, so I calculate F parallel using the same method we usually do. Okay, so F parallel will be the sine of 40 times the force of gravity, 435 newtons. so 279.612 newtons. All right, so now I know that. Can I calculate the net force? I have mass, because I calculated it before, and the question told me the acceleration is 0.250 meters per second squared, okay? So I can calculate F net by going m times a. Okay, so 11.09 newtons. And that would be down the ramp. Okay, how do I use that to get the force of friction? Emma.
Fd plus F friction is equal to the F net. F net is equal to the sum of all forces.
F net is equal to the sum of all forces, right? Okay, F parallel plus the force of friction. Okay, so if I want to calculate the force of friction, that's going to be F net minus F parallel, okay? And they're both in the same direction, so 11.09 minus 279.612, okay? And that's going to give me my 269 newtons up the ramp. And I know it's up because I made down the ramp positive, and if I put that in my calculator, it's going to come out negative. Okay? Negative is up the ramp in this case. Okay? Questions there? All right. Let's take, let's say so looking at 5 and 6, these are both questions that are going to have some vector stuff related to them. 5 is considerably easier than 6 because everything's collinear, but 6 is going to involve you doing some vector diagram stuff. Okay. All right, so on number 5, we've got a level floor. We've got a big crate, okay? And we're looking for the mass of the crate. We don't know what it is. What we know is that there's 300 newtons worth of force forwards from one person, 250 newtons worth of force forwards from the other person, and we know that friction is opposing with 175 newtons worth of force, and we know the acceleration of the crate. Okay, 1.57 meters per second squared, also in a forward direction. All right. What can I calculate right now with the diagram? I can calculate net force. All right, so that's what I want to do first. Okay, I need to get net force, so that's going to be 300 plus 250 minus 175. Okay, so 550 minus 175. Okay, so 375 newtons. Forward, okay, is going to be my net force. What do I do with that?
Divided by acceleration.
Divided by acceleration. Okay, so now I do F equals m times a, right? So F net divided by acceleration will give me the mass. So 375, okay, divided by 1.57 should give me that 239 kilograms. Okay. All right. How are we doing on 6? How many people have done 6? Okay. Are we ready to go over 6, or do we want a few more minutes on 6? 2 more minutes? Okay, done. 2 more minutes on 6. All right, just so you know, this was an exam question about 6 or 7 years ago, and then I changed it to be like 2 dogs fighting over a chew toy, and like it's basically the same thing. Every exam I have a question kind of like this, okay, where there's going to be some vector addition to find net force and get acceleration from there. All right, so we got 2 children making a snowman, and they're pushing the snowball into position. Okay, we know the snowball has a mass of 50 kilograms, and one of them is pushing 15 degrees west of north with 130 newtons. and one of them is pushing due west, 110 newtons. Probably a more efficient way to move that, but that's what they're doing. Okay, there's my free body diagram. Can that get me anywhere other than having identified those two forces? Not really. Okay, if I want to find the net force, I have to find the vector sum of these two forces by drawing the vector diagram. So I'm going to take the 130 first, and we'll say that that's 15 degrees. Okay, so this will be x, this will be y, and this will be 130 newtons. Okay, and then 110 newtons due west, and that means that my net force will be right here. Okay, that will be its vector, this will be y, and this will be x. Okay, everybody with me so far? Alright, so we got to calculate all of our x's and y's. Okay, so red x is the opposite side, so that'll be the sine of 15 times 130. Okay, 33.65 newtons, and that's west. Okay, and our y component is the adjacent side, so cos of 15 times 130. So 125.57 newtons north. Okay, for our 110, it's just due west. It doesn't have a north component, so that part's easy. Okay, and now we can get our resultant's x. Our resultant's x is going to be 110 plus our 33.65. Okay, so 143.65 newtons west for blue x. Okay, and blue y is just going to be 125.57 newtons north. All right, what do I do now? I just did finding x's and y's until I'm dizzy. What do I do with them? Yeah, now I do Pythagorean theorem. Pythagorean theorem will get me the hypotenuse, whose magnitude at least is the net force. Okay, so F net is going to be the square root of 143 squared plus 125 squared, obviously with all the decimals in place. Oh, and I don't even have the other one in there. Plus 143 squared. Okay, so my net force is 190.79 newtons. Okay, I still need the vector on that, so I got to find theta. The way I drew that triangle, that's going to be the 125 over the 143. Okay, again, with all the decimals in there. Okay, so we're looking at 41 degrees, 41.16. And for me, that's going to be north of west. Okay, what did they want? I just calculated net force, but what do they want? They want acceleration. Okay, so then I've just got to take what I calculated with Pythagorean theorem, the 190, yeah, and divide it by 50, okay, which will give me that 3.82, but sorry, we decided it was only two significant digits, meters per second squared at 41 degrees. For me, that's north of west, but you could also have at 49 degrees west of north, Either one of those would be acceptable as they point the same way. Okay. Is this making some sense? All the vector stuff? Okay, like, I'm not gonna get crazy with vector stuff, like, if I'm gonna ask you to do this on a test, that's as many vectors as you're gonna have. Okay, it's gonna be just like the vector addition question on your Unit 1 exam, right? I'm not gonna go into a whole bunch of craziness and have 5 different forces that you have to put tail to head, okay? That's not a really fair assessment of the situation. All right, tomorrow, we are gonna be doing our lab, so we're gonna be setting up the tracks and the pulleys and the carts, okay, and everything. So make sure you've still got the SparkView app on your phone. You're gonna need that, okay, to record the accelerations of the cart, given the different applied forces that will be acting on them tomorrow.